Yes, this slide is our repeat, but this shows all of our reactions and those initiation, propagation, termination rules to think about and consider. So, moving forward, since you got 10 seconds to have looked at that and now memorized it, why look at radicals? So, if I'm going to look at trying to make, say, this alkene, and the premise of why isn't super important, but we need to make that. Okay, how could I go through and do it? Well, there's a variety of ways we could go through and do through substitution reactions, right? So if I had that bromine on there, I can now add a strong base, okay, or add just a base in this case, and that base could go through, remove a hydrogen, and eliminate and give me that product. But that means I have to have this alkyl halide. Well, one of the problems that synthetic chemists will encounter is that just because you know one step of this reaction doesn't mean that that material, and we can go through and color it slightly differently, that this material, this alkyl halide, exists. Okay, that material may have very limited commercial availability. Okay, so if it is limited in its availability, I then have a new synthesis and I have to go through and make that material. And so what we'll end up finding is that most of our organic reactions start all the way back at an alkane, because that's what's being produced when we look at our source for nearly 90% of our chemistry reactions. That was an entirely made up statistic for the record, but I believe it's probably something stupidly close to that. 90% of all chemistry that we end up doing or using is rooted in petroleum. This is one of the reasons why it's stupid to use petroleum to fuel our cars, because we are literally burning up our ability to make things. We're turning it into CO2 that we don't have the chemical capabilities right now to efficiently convert back to our alkanes. Okay, so that's one of the biggest, or one of the problems, let's not call it the biggest, one of the problems with using gas in our commercial society is because we're getting rid of our ability to actually convert and make other things. So alkanes is our core. That's usually where everything starts. So we have to know reactions on how we can convert those alkanes into larger structures or cyclic structures or all those other pieces. Okay, radicals just happen to be one of the tools that allow us to do that. Because alkanes are so inherently unreactive, we need to get them to react. To do so, what I can do is throw Br2 or bromine at that material with the presence of light. Bromine will immediately go through with that light and form our bromine radical. That bromine radical can now, because it is so reactive, react with the most available thing on our alkane, which is going to be hydrogens. Which hydrogen does it go after? Well, because of the stability of intermediates, and we'll see this in a second, the bromine radical is going to go through and what is referred to as abstract is going to remove a hydrogen in there. Okay, why? When it removes that hydrogen, we form the most stable radical intermediate. Okay, and because bromine radical was so inherently stable to begin with, it effectively gets to decide which hydrogen to remove. If our radical initiator, in this case our bromine, okay, was unstable, then it's just going to react as fast as it humanly can to remove whatever it can to stop being a radical. Okay, and so we end up getting a non-selective reaction. Bromine is the kind of perfect halogen because it is very selective, but at the same time pretty fast. Okay, and that's why we go through and use it. Okay, and a fast reaction. Once we've got that radical, now we'd say, okay, what's the next most likely thing for it to encounter? Before you start saying, well, another bromine radical, that's actually very unlikely to form. Because remember, the radicals are small concentrations. So the next most likely thing to encounter is not going to be a bromine radical, but it's probably going to be starting bromine compound. This now runs through another radical reaction where we end with our bromine substitution, and we'd have more bromine radical, which could now continue the reaction. Okay, so a lot of the mechanism behind radicals is following concentrations and recognizing that our initiation happens in very small concentrations, which means those species aren't going to be super prevalent, and that our terminations also are happening in very small concentrations, which means when I'm looking at kind of the meat of the mechanism for a radical, it's always propagations. Don't start initiating things right away. Don't start terminating things in your mechanism because they just aren't likely to happen. When can you use those? Well, if you don't have a radical to start, you need an initiation. Okay, when can you use the termination? When the question says, which of these are a valid termination, then you can use a termination. Okay, the vast majority of the mechanism that you should be looking at should be propagation steps. Okay, so back to this, bromine, very selective, very fast, so phenomenal reagent for our halogenations, okay, or trying to put that single halogen on there. There are other halogens. We have chlorine, we have fluorine, and we have iodine, okay. If we go through and look at those, chlorine does work, okay. It is faster than bromine, which is actually kind of cool. So why don't we use chlorine if it's faster? Well, it's faster, but it's highly imprecise. The chlorination reaction will react with any and all hydrogens. And so depending on your class or where you were taught radicals in the past, if you've retaken this class, is you may see calculations where you would determine the major product based off of a formula that allows you to determine how the chlorination kind of differentiates. And ultimately it doesn't differentiate, but you're given experimental results that get tied into a formula to say how much you get of each of those materials. I think that's a waste of time personally, okay? And so I don't make you go through and do that, but I'm pretty sure Cardi does have examples of that in the textbook, and there might be questions in smart work, but I really just think it's a waste of time, okay? So I'd be surprised if I even asked it in the smart work. Okay, so the chlorine with light, ultimately the big thing you need to know there, it's not selective. Fluorine and iodine are also valid halogens. Fluorine is too reactive. What do we mean? It reacts incredibly fast. So fast that if I mix fluorine with an alkane, it literally explodes. Okay, and I would get a massive explosion of probably glass shrapnel, depending on what container I was using, back in my face, and that's not desirable, okay? So we don't use fluorine as a reagent in this fashion because it's too fast. It's so unselective that it doesn't work, okay? Iodine is too slow, okay? Iodine is so selective that it only forms that most stable radical, which is fantastic. I would get a much higher yield of the product that I wanted. Bromine is kind of that balance, so we're losing some, okay, but we don't lose a lot. Iodine is so incredibly slow and so incredibly selective that it only forms our desired radical and thereby our desired halogen or halogenation reaction. However, it is so incredibly so that the lifetime of the reaction would be well longer than my lectures and the amount of time that I've spent already talking about this slide. So we're going to go ahead and move on and look at some energy diagrams. That slowness has to do with those activation steps. So if we're going through and looking at bromine radical versus chlorine radical, that speed has to do with the activation energy for either the formation of our more substituted, so our substituted radical, or our less substituted radical. Okay, so our more stable or our less stable. When we go through and look at the chlorination, we're still going to see that. Okay, the more stable is still lower in energy than our less stable. So why don't we see a preference one way or another? Okay, well, that preference is going to come into the activation barrier. That activation barrier is your transition state. Okay, and that's largely what drives these. Okay, why is that really shifting so much around? Well, it's probably not so much the transition state, it's the balance of where the reactants and products are. If we go through and look at the bromination reaction, you should notice that that is an endothermic reaction, which means that transition state, according to the Hammond postulate, which we keep floating out there as a term, is closer in energy to our products. Well, because our products have vastly different energies, the transition states now have vastly different energies. If we go through and look at the chlorination, it's an exothermic reaction. So it's going to release heat as opposed to needing heat to cause it to work. Because it's an exothermic reaction, our transition states are now closer in energy towards the reactants. Why does that matter? Well, the reactant isn't different for either of these pathways. Okay? Which means the difference in energy for our transition states is negligible. Okay? We get virtually no difference. That might actually be right. Which means when we go through to look at our products, we're really going to get a mixture of both, because both are equally forming. And because it's an exothermic reaction, the reverse process is very unlikely to happen, and we don't see that reversibility. Okay? Whereas in the bromination, if we had potentially even formed that less stable one, this process is reversible. That reverse reaction has a very small activation energy. We could theoretically reverse that, and it's going to start to reform only our most stable, because that's going to be the least reversible of them all. Okay? So radical reactions in these energy diagrams end up coming into play to really kind of address the Hammond postulate. It also helps us see that the bromination reactions are what is known as selective, because we're driving for that more substituted radical. It shows that our chlorines are less substituted because there really isn't a preference, because the activation barriers are the same. And because it's exothermic, we're irreversible. So all of those terms kind of float together into one giant freaking mess of a pot. And that's largely why you end up seeing Hammond postulate and all of these things jump in for radical reactions, which is also why radical reactions are very often taught early on, because it shows all of these concepts. I think it's too much of a mess to do it all at once, and so I pull it out and trying to subtly bring in those concepts as opposed to jamming it all in at once. So the big line, party line here, is if given a choice for your synthesis, you want a bromination reaction, not a chlorination. Okay? So, next part, stereochemistry. What would our stereochemistry of our radical reactions come out to be? Okay, so now we're looking at kind of a complication of this. Well, let's go through and walk through this mechanism again. So if we go through, we have our Br2. I've stopped showing lone pairs, so I'm going to try and do that because we're showing a full mechanism here. We're going to show our fish hooks. We're now going to form a bromine radical. This bromine radical is now going to float around in solution until it potentially encounters something useful. Okay, and by useful, that is an odd term, because the most likely thing for that bromine to encounter is actually going to be more bromine. And so what we would expect is another radical reaction. Why is this radical reaction not something really worth discussing? We're going to form Br2 and, well, bromine radical. Okay, so we end up reforming the exact same thing that we started with, so it ends up being a not useful thing to really address. But the vast majority of our bromine radicals are probably going to be stuck in this kind of endless loop of just jumping bromine radical to bromine molecules and just bouncing around. Eventually, what will happen, and that is productive, is our bromine radical will encounter our alkane. And again, what we need to consider when we're looking at our radical reactions is the most available thing in that structure. We're trying to find electrons to react with. Well, the most available thing is for sure going to be our hydrogens, because our hydrogens are on the outside of the structure. But now the question becomes is which hydrogens? Because bromine is selective, okay, and we'll just use it as that term, what we would expect is to form the most stable radical. So the result of that is that we end up forming the bromine with hydrogen, and we now have the formation of HBr, which we tend to ignore because it's not organic. And then we would also have, a bromine radical, a carbon radical. This carbon radical is now going to float around in solution until it encounters the next most likely thing. The next most likely thing for it to encounter would be another molecule of bromine, and we would have our radical reaction propagate, but in this case, instead of propagating and kind of going nowhere as our previous propagations went, we now actually have a final product with the bromine attached. Okay, so we've now walked through our mechanism, and we've got, all of the different stages kind of outlined within this, and we could start to consider some of the reactivity. So what are we considering with stereochemistry? Well, here's our final product. Do I care about stereochemistry? Yes, there's a stereo center there. That has 4 distinct things connected to it, which means stereochemistry or optical activity is something that I should be at least considering. If we backtrack through our mechanism to decide when and where that came about, okay, well, that actually nice and easy came about in the previous step. Okay, in that previous step, we had the radical go through and do its reaction. Okay, well, where were the electrons that made the radical? Okay, this is where it's important that we remember that we said radicals approximate carbocations. What does that mean? That single electron is floating in a p orbital. Where is the p orbital? It is both above and below the plane of that alkane, which means the radical could have reacted in the upwards fashion, making the bromine wedged. It could have also reacted in the downward fashion, making the bromine dashed. So I would technically be getting 2 products here. Okay. Which may not be ideal if we consider systems, but we now at least have a species that can react. Okay, so we could go through and draw both of them, or we could go through and say plus an enantiomer. We can really only say plus an enantiomer, assuming there wasn't another chiral atom in the molecule. If there was another chiral atom, then the relationship between those 2 products is diastereomers, and we would have to draw it out because we can't just say plus diastereomer. There's too many different possibilities that could align with that. Okay, and so stereochemistry, it can show up, but because we're equating to a carbocation, the electrons are both above and below the plane of the molecule. Those systems are going to align so that you're going to get 2 products, which means when we get to optical activity, there's no optical activity, okay, because we're getting a mixture of those 2 materials, and so we're ending with either achiral or racemic products, depending on how we want to address it. Okay. Next thing we want to throw in, what about allylic chemistry? So if we go through and look at an allylic position, so now all we've done is added a pi bond. How does this change things? Okay, well, our Br2 is still going to become a bromine radical, so I'm not going to go through and show that part of the mechanism. But now what we have to do is consider stability of our cations. Okay, so if we go through and look, we're trying to do a substitution, and I'm just going to draw 1 hydrogen on each of these positions. And you'll understand why I'm drawing that hydrogen over there. And then we have the green hydrogen. So really, there's only 3 types. Okay, we've got our blue type due to symmetry in the molecule, our internal. And we have a green type, a purple type, and I can't remember if I said it, a blue type. Okay, I'm drawing them all up because our bromine radical is on the top side. So if we went through to do our radical reaction, we could do the radical reaction with purple. We could do the radical reaction with green. Whoops. Oh man, we'll just pretend that arrow isn't there. It's not in a place where I can easily erase it. Okay, and note that we're going to have 3 curved arrows in each case. And this would end up with 3 possible products. Okay, which of these is the most likely one? If you've been doing pretty well with resonance, okay, and evaluating stability of things, in theory, you don't have to draw these things out. At this stage in the game, well, actually, I don't know when you're watching this video, but I would argue you should be drawing all of these things out so that you get used to these patterns so that you don't have to draw them out in the past. Okay, so we've got these 3 possibilities that could come out of this. Why does this become an issue? Well, we have to pick the most stable one for our bromine. Which of these is the most stable? We might go through and say the blue one is secondary, the purple one is primary, so the purple one shouldn't form. And then the green one is secondary. Is it secondary? Okay, it is connected to a carbon, it's connected to 2 other carbons, but that carbon is sp2 hybridized. Okay, and as we talked about in substitution, when we've got that sp2 hybridization, it doesn't make sense to refer to it as secondary because the chemistry is drastically different. How drastically different is it? Well, the secondary one with its location has a resonance stabilization, and of course I showed that as heterolytic. Oh, come on. Shows how often I practice this. We have resonance, and for those people being like that were hoping that we didn't have to worry about resonance because we were doing homolytic bond cleavage, you can still resonate with radicals. It is still a perfectly viable option. This is secondary plus resonance. Okay, so secondary plus resonance makes that one incredibly stable. Okay, which would mean for this particular reaction, we would expect a very high concentration of the bromine going to the blue position, okay, not to the purple. And then the green one being sp2, do we have sp2? Are sp2 cations, and really it's not even an sp2 cation, but sp2 cation formation, was that allowed? Okay, and again, if you remember back to when we talked about SN1 and SN2, or even the lab, no, that is not allowed to form. So if we go through and look at this, we're really only getting 1 reaction. This becomes a bit more useful to reference, okay, because now we can go through and run substitution reactions, not with just alkanes, but with alkenes. Okay, and this is where sometimes people will think about this as a new reaction. I would argue it's not a new reaction. The chemistry that you're reacting, the functional group that you're reacting, is still an alkane. All that's changed is that we're saying that alkane position at the allylic spot is the most stable radical. So it's the most likely to form. Okay, so that allylic chemistry does come into play. Remember, the allylic chemistry came into play with carbocations. Radicals are roughly carbocations. It all kind of aligns. Okay? So, I'm going to clear all of that away and address the next issue. So, there's our reaction. We said very cleanly that we should get this product in probably higher concentrations than we should see anything else. But what happens if I now change this reaction? What should I get now? And for those of you being like, well, what the hell did you just change? I didn't see anything. All I did was erase. Okay? That H nu at the bottom is light. What happens when I erase H nu? Now there's no light. So now what happens? This is this unit, Br2, because it is no longer being caused to break homolytically with our light, cleavage light, now is going to act as an electrophile. And why does this become problematic? Do we have a nucleophile in that pi bond? Yep, we do. And we now have the potential to go through and form with the exact same reagents, the exact same chemicals, and we would get the situation where those bromines are now added across the pi bond. Okay, that becomes a problem. So if I want a radical reaction to happen, how do I minimize the effect of this heterolytic cleavage? Because again, the radicals are very small concentrations. So one way we can get through and do this is not use Br2. Okay, we can switch it up to a different reagent. And that's where NBS comes in. So if we really want to shift our reaction more towards the substitution and not that electrophilic addition, we need to control the concentration of bromine a little bit more. The best way to go through and do that is this reagent NBS, N-bromosuccinimide. It has a very, very reactive bond on it, that nitrogen-bromine bond, because we now have two electronegative elements connected to each other. And what NBS will do is it will react in such a way that it produces very small concentrations of Br2. If those concentrations are small enough, we can now start initiating a radical reaction. The radical reaction will run, we'll get our allylic substitution, and we minimize the effects of our electrophilic addition. Okay, but if we just throw tons of concentration or tons of Br2 into this solution, we increase the odds of getting the electrophilic addition. Okay, so radical substitution reagents, we get 3. Br2 and light, which is our most common reagent. Okay, this is only going to really go at most substituted positions or most stable carbocations. Chlorine and light is not a very likely one to see because it goes at pretty much all positions. So that's a bad reaction to run. It does sometimes show up as a question where it's, where can the substitutions happen? Well, it freaking happens everywhere. That's what chlorine does. But that's where that question encounters. And then you get NBS and light. And NBS is going to do a bromine substitution at the allylic or benzylic position, which is just to limit the access to the electrophilic addition, which is going to set us up for our very next video, as I lose my voice, which is going to be looking at our radical addition reactions.